2.1 Properties of Matter. In this section, you're going to identify physical properties and physical changes. You're going to distinguish intensive properties from extensive properties, and you're going to differentiate among the three states of matter, very much like we did in Chapter 13. Below the objectives, you see the vocabulary for this section. Okay. Why are windows made of glass? In this lesson, you will learn how properties can be used to classify and identify matter. We talked about glass in Chapter 13. Now we're going to talk about how it's made and what properties it has.
Hello, it says here you sell double glazing. Do you have a piece in stock? Let's say 4x8 meters? Only in frosted glass. They only have in frosted glass! No, I'm sure they'll notice it. You installed straight away. Oh, brilliant. How much is it then? Including putty? Not okay. No problem, I'll keep looking.
It's such a simple, routine act of everyday life, opening and closing a window.
Yet I'm not really sure how or why this window glass started out as a heap of sand. So how do you go from sand to a perfectly clear window?
Are you still here? The story of windows starts here, way up here, 60 feet off the ground in Carlisle, Pennsylvania at PPG. These are giant, massive silos that hold the key ingredients to glass.
The main one, sand. Every day, 800 tons of it are fed into the building here, and then mixed with two elements critical to the manufacture of window glass: soda ash and lime, or sodium carbonate and calcium carbonate. They lower the melting point of silica sand and alter its basic molecular structure.
These chemicals soften the glass. They make it easier to melt, they terminate the silicon-oxygen chains, and make a more manageable glass to work with. And that soda-lime silica glass lies at the heart of every window.
Now, all of our raw materials have been mixed together and dumped into tanks like these, where it's a cool, low 3,000 degrees. It's actually hotter than molten lava. And it will take 3 days for a single molecule of sand to get from this point all the way to the other end of the factory, where it actually starts to resemble a sheet of glass. All right, so we're wearing this protective garment for a reason, right?
Right. Wearing Kevlar gloves, fire retardant.
We're dressed like big oven mitts.
Right.
Yeah, it's pretty hot where we are, but it's going to get a lot hotter in a second, right?
Yep.
So let's rake.
Steve Anderson and I have to rake this batch quickly. The goal? Well, don't let the rake melt first, and spread out the mix to reduce air pockets that might form.
I see you're pulling that whole raft over the wall.
Yeah, it's like tapping.
Yeah, just like that.
It doesn't take long for the batch to start looking less like sand and more like an overflowing volcano. The only way to see this river of glass is through these polarized metal masks. Without them, your vision will be, well, gone. There, inside that shiny surface on the bottom, that is liquid glass. For 10 hours, the molten mix is superheated behind thick walls to allow gas to bubble up and out. Bubbles drive glass makers nuts. After all, nobody wants to look out a window you can't see through. There is only one way to create plate glass without bubbles, and more importantly, flat on both sides.
If a window isn't flat, it'll distort your vision, like a wrong pair of glasses. But making flat window panes is hard, and it used to be done by blowing giant glass bubbles, cutting them open, and laying them flat before they solidified. But they didn't end up perfectly flat. So since 1959, glass has been made by pouring molten glass on a river of liquid tin.
The surface of any vast, undisturbed liquid is flawlessly flat. Tin ingots are melted down, creating that perfectly flat surface. The glass pours onto the tin and immediately begins to cool.
Tin and glass don't mix. Like oil and water, the lighter glass floats on the denser tin. And the result is a system where the liquid glass and liquid tin start at high temperature at one end of this giant river, and they cool. They're cooled deliberately until at the end, the tin's still liquid, but the glass is solidified.
Compared to glass, tin's melting point is low. By the time it reaches this stage of the assembly, the glass hardens, floating on top of the molten tin like driftwood on water. Still very hot, as in 1,000 degrees Fahrenheit hot. The glass moves down the line in one long continuous sheet. It stretches a quarter of a mile, and because of its length and temperature, it's surprisingly elastic and strong enough to really beat on.
This glass, almost as hard as you want. You won't break that glass. It's extremely strong and it's pristine.
Steve, I think you've actually proved your point there. So from here to there, you need to bring it down about 100 degrees.
100 degrees, and that's why we have such a long cooling conveyor to allow it just to cool down naturally.
A robot then cuts this long ribbon of glass into slabs that run about 12 feet across.
These long pieces of glass have been cut, and in a moment they'll be packaged and then shipped to their distributors, where they'll be turned into windows.
To make windows, we haul glass down the road a ways to a window factory called by Winco in Morgantown, Pennsylvania, where on average 400 sheets of plate glass stream in all day, destined to become window panes. Working with this stuff can be very dangerous.
Now this is kind of like Kevlar?
Yeah, so that is Kevlar material.
This is the same stuff they use in bulletproof vests.
Yep. When you're pulling them off the table, you pretty much, that glass is right at your waist, right at your leg area, so we want to make sure that's protected.
Always put your Kevlar sleeves on first. Andy, dare I ask, has anyone ever been cut?
Yes.
I had no idea that Dickie was making a comeback. Lou, suit up, my friend. You gotta put it on. So you got your Dickie on, you got your Kevlar sleeves, and you really are kind of ready for a kind of a Liberace thing in Vegas. It's nice, with a little Michael Jackson. It's very impressive.
Coming up, we make our window, and one that can weather a hurricane.
It really does hold.
The mass of an object is a measure of the amount of matter that object contains. Here are some examples. We have a 1-ton weight. We have a red bolt that has a 10.5 gram mass. We have two boxes that both have a mass of 100 grams. That's how much there is. Now notice one box is much bigger than the other, so even though it has the same mass, it doesn't have the same volume. Therefore, they would have different densities. Percent by mass. If you take 10 grams of sucrose, which is table sugar, and you add water until the mixture of the sucrose and the water is 100 grams, that's a 10% by mass because they have 10 grams of sucrose over 100 grams of solution. 10 divided by 100 grams times 100 for the unit is 10.0% mass. Extensive properties, intensive properties. Students see this and they freak out. They're like, I've never heard of such a thing, but you have. Extensive properties are what we used to call quantitative properties. They depend on the amount of matter, so there's going to be a number in them. Whereas intensive properties, which you probably called qualitative, only depend on the type of matter. Now, here are some examples of extensive properties. I have the mass of 30.06 grams of crystals. I have a volume of water at 66.0 milliliters. I have a screw that has a length of 5.12 centimeters. I have the pressure being 765.3 millimeters of mercury, and I have a temperature of 37.0 degrees Celsius. Now, if you remember back to the measurements, you can tell they're all going, what their significant digits are going to be. Since they all have decimals, I start at the leftmost number that's not a zero, and I count to the right. So 30.06 is 4, 66.0 is 3, 5.12 is 3, 765.3 is 4, and 37.0 is 3. Intensive properties are things that you don't measure necessarily in numbers. Like you wouldn't say you have a 7 blue. So color is an intensive property. The melting point of a substance is an intensive property because it doesn't usually change. Same thing with what you're seeing in the third one, which is salt dissolving in water. We call that solubility. It is the ability for water or another solvent to dissolve a substance. In this case, it is breaking apart the salt molecule or the salt ions. Density is another one. Density, what you see there is carbon dioxide is in the container and the bubbles are air. They're less dense, so they will float on the bed of carbon dioxide. On the bottom, we have the pH scale, which is a measure of how much acid or alkaline is in a substance, and those are all intensive properties. Matter that has uniform and definite composition we call a substance. Now I'm going to show you a few of them. The first one are the elements iodine, bromine, and chlorine. I can tell that they're a substance because I can write their formula. The next one, that looks like sugar cubes. It is. The formula for sugar or sucrose is C12H22O11. H2O, water, that's another substance. That is sulfur, S. The blue crystals are copper 2 sulfate, which is CuSO4. This last one's kind of tough. They're all different. Some people think that they're styrofoam or whatever, but they're not. They're actually solid carbon dioxide, which we call dry ice. Now, all samples of a substance have different physical properties. Even though those samples, you see bricks, you see pellets, you see shavings, even though they look different, they're all the same. So the word is all samples of a substance do not have different physical properties. They have similar physical properties because they're all carbon dioxide, no matter what they look like. A physical property is a quality or condition that can either be observed or measured without changing a substance's composition. Observing is when you will take a qualitative measurement, and measured is when you take a quantitative measurement. So observing is going to be for intensive and measuring is for extensive. Now what you see there is a crayon rainbow, which is when you take solid crayons, you put them in front of light, and the heat from the sun will cause them to melt to make the rainbow. Now, hardness, color, and boiling point are properties. Melting is a phase change. That's a physical change, not a property. Melting point is a property. Melting itself is a change. Look at the table. What is the melting point of bromine? So I go halfway down. I see bromine. It's a liquid, reddish brown. -7, 59. -7 is the melting point, which is right here. So I now know that's the melting point. The yellow solid that melts at 115, if I go down there, there's only one solid that's yellow and melts at 115, and that would be sulfur. Is the following true or false? Physical properties can help a chemist identify a substance. That's true. That's how you did 7 and 8. Circle the letter that is not a physical state of matter. Now, we've already done physical states, and we said there's gases, liquids, solids. Well, the odd man out is water. Water is not a physical state. It's an example of matter. Water can be a gas. Water can be a liquid. Water can be a solid. So when you're looking at that, that is not a state of matter. It's an example of matter in the 3 states.
Do you know what water air, and rocks all have in common? They are made of matter. Matter is something that takes up space. Now, you might be wondering why they all look so different if they are made of the same thing. But the truth is that everything around you is made of matter, just in different shapes and forms. Matter is made of tiny particles called atoms. Matter can be grouped into three main states: solid, liquid, or gas. To figure out which state of matter something is in, we need to examine its properties. A property is the way that something is that we can measure. The physical properties we will look at to determine state of matter are shape, mass, and volume. Mass is the amount of matter in an object. Volume is how much space that matter takes up. Solids are easy to recognize. Rocks, apples, pencils, and plants are all examples of solid objects. A solid object has a definite shape that doesn't change when you move it or put it in a container. They also have a consistent mass and volume. This is because the atoms in a solid object are packed closely together, so they do not move around. A solid will change shape only if forced, for instance, if it is broken or smashed. If you look around, you can find many examples of solid objects. Liquid is the next state of matter. Liquids have a definite volume and mass, but they do not have a definite shape. The atoms in liquid are still close together, but unlike the atoms in a solid, they can move around. This allows the matter in a liquid to flow. Because liquids don't have their own shape, they take their shape from their containers. The same amount of liquid may look very different in a glass and spilled on the floor. You can find examples of liquids around you too. Water, milk, and juice are just some of the liquids you might find. The third state of matter is gas. Gases have a definite mass, but they do not have a definite shape or volume. Like liquids, gases take the shape of their containers. Unlike liquids, gases will spread out to completely fill the container they are in. If a gas is not in a container, it will keep spreading out indefinitely. This is because the atoms in a gas are farther apart than atoms in a solid or a liquid, and so they can move freely. The air you breathe is an example of a gas. You might have noticed that you can't really see air. Often, gases are invisible, but they are still there. There are many different types of gases in the Earth's atmosphere, like oxygen, nitrogen, carbon dioxide, helium, and water vapor. Sometimes matter can change from one state to another. Water is a very good example of this. When water is frozen into ice, it is a solid. When it melts back into water, it is a liquid. When water evaporates into water vapor, it becomes a gas. Matter in all its states is everywhere. See if you can find solids, liquids, and gases around you.
Now, complete the table about the properties of three states of matter. Use the terms definite, indefinite, easily, not easily. So the first one is the property is the shape. The shape of a solid is definite. It does not change. The shape of a liquid is indefinite. It will take the shape of its container up to its volume. The shape of a gas or vapor is indefinite. It will completely fill its container. The volume of a solid is definite. The volume of a liquid is definite. That's why when you drink out of a glass of water, eventually it empties. And the volume of a gas is indefinite. It will then take, once again, the shape of its container. Solids have definite shape, definite volume, and they're not easily compressed. Same thing with liquids. Even though they have an indefinite shape and a definite volume, they are not easily compressed because the particles are so close together. Gases are vapors because they are so far apart. They are easily compressed. Now, arrange the particles in the proper arrangement for each state. So a gas is C, spaced relatively far apart. A liquid is B, they're close but free to flow. And a solid is A, it's packed tightly together, it does not flow. Here's an example of a gas. You can see the particles are far, far apart. Here's an example of a liquid. Particles are closer together, but they will flow. So if I were to turn the glass on its side, watch what happens. The particles flow out. And last but not least, the particles of a solid are very close together and they do not flow. So when I dump it out, it doesn't change shape. It just comes out the same shape it was inside. 13. The words gas and vapor describe the same thing. That is false. The difference between a gas and a vapor is a gas is limited to substances that exist only as gases at room temperature. A vapor describes the gaseous state of a substance that is generally a liquid or a solid at room temperature, as in water vapor. Water is a liquid at room temperature. When it evaporates, you call that water vapor.
In the bottom here, Billy, what's happening to us?
It's evaporating.
Well, it's actually, evaporating is sort of correct. Actually, you should say boiling. Boiling and evaporation are pretty much the same, except boiling takes place faster. You have heat down below. How do you know it's boiling?
Because you got the stove on.
I see. I thought maybe you were going to look at the little spout there.
Wow, there's steam coming out.
Oh, wait a minute. What?
There's steam coming out.
How do you know?
Because I can see it.
No, what you're looking at is not steam. This is a mistake a lot of people make. And if you want to be scientifically correct, we should use the correct term. Those are little tiny droplets of water. And you should say water vapor. Steam is right here, right at the end of the spout. Can you see it?
No.
Steam is invisible. See, when you change water to steam, it's actually in the gas form. The molecules are dashing all around, they're not together. When you put them together, you get this stuff, which is water vapor. Let's change the water vapor back to steam, and I think you'll see.
How do you do that?
Well, all you have to do is take the stove and hold it under the water vapor and heat it up again. Here you go. Okay, hold the heat right under the... See, it's gone, right?
Where'd it go?
Because you're heating it up and changing it back to steam. Now take it out of the way. There it is. Showing that you're heating those little droplets and changing them back to steam again. So the next time you see that white stuff coming out of a tea kettle, what are you going to say, Carl?
It's water vapor.
Right.
Mixture of solid water vapor and gas particles in a suspension. The solid particles are held in the vapor, which we say they're suspended.
You don't want to watch? Dad. Are you recording, Mark? Yep. Are you dead on? Wow! Come on, Graham. Come on, Graham. No, I can't. Oh, these are homemade by my brother. Oh, really? Yeah. Dude, that teal one is something to... That's
Change alters a given material without changing its chemical composition. Some words that we use to describe physical changes are boil, freeze, condense, dissolve. Those are reversible physical changes. So I can add energy to get them to happen, or I can take out energy out to get them to go the opposite way. Grind, cut, break, and crush are considered irreversible physical changes because if you break a glass, you're not going to be able to unbreak it. Whereas if you freeze water, all you have to do is put it out and it will melt back into regular water. What is true about all physical changes involving a change of state? All physical changes that involve a change in state are considered reversible. Now, I want you to look at this picture below. You see a glass and you see a spoon. Now watch. What you saw there was something called the gallium spoon. Gallium is a metal that melts just above room temperature. It melts about 30 degrees Celsius. Well, that's just warm water, which is obviously above 30 degrees Celsius because he dipped his fingers in there to show you that it wasn't boiling hot and it wasn't some kind of acid. So what happened there was the spoon melted into liquid gallium. Now, when you finish a section and you've gone over the notes and you've done your reading, you should always go back to the first page that shows the objectives and the vocabulary and ask yourself, can I complete these objectives? So if somebody said, can I identify physical properties and changes? Can I distinguish between intensive and extensive? Can I differentiate among the three states of matter? Can I give a definition for each one of those terms? If you can define each one of those terms and give a complete objective, then you are ready to move on. 2.2, mixtures. We're going to classify a substance of matter as a substance or a mixture. We're going to distinguish between homogeneous and heterogeneous samples, and we're going to describe two ways that components of mixtures can be separated. Most samples of matter are mixtures. That is true. A mixture is a physical combination of two or more substances. Now, is the following sentence true or false? A heterogeneous mixture is one that is completely uniform in composition. Now, completely uniform will be the same throughout. So that's a false statement. And I'm going to show you this in this little slow motion of oil mixing with water. When they mix, you can see the two parts of the solution and you can almost see the colors are different, but the main thing is they're not going together. So no matter what you do, eventually they're going to separate. And when they separate, that's called heterogeneous. And in a heterogeneous mixture, you always can see more than one thing. That means they're not uniform in composition. I can see the globules of oil and I can see the water that it's in. So that would be a heterogeneous mixture. Another name for a homogeneous mixture, we call those solutions. Circle the letter of the term that describes a part that has uniform composition and uniform properties. Well, we call that a phase. So in a solution, you have one phase. In a heterogeneous mixture, you have two or more phases. So here we go. 6a, heterogeneous always have one phase. If you look under the word one, you see a test tube and a blow up of the molecules inside. That is a homogeneous mixture of acetone and water. And the fact that they are mixed together, you do not see different layers. But on the right, is a heterogeneous mixture where there are two or more layers. The top layer there is water, and the bottom layer is a dense compound called methylene chloride, but you can definitely see the line between the two layers. So that's the difference between heterogeneous and homogeneous. Homogeneous will have one phase, heterogeneous will have two or more phases, two or more different areas. In general, what's used to separate mixtures? Differences in their physical properties, because mixtures are physical combinations. So what you do is use a difference in their physical properties to separate them. The process that separates a solid from a liquid in a heterogeneous mixture is what we call filtration or filtering. And on the right, you see how we would filter in lab. Get yourself a funnel, get yourself your mixture, put some funnel paper inside or filter paper inside, and you pour it through, and the solid would stay in the filter paper and the liquid would go through. That's really how coffee works, because the coffee grounds stay in the filter and the liquid soluble coffee will then go into the water.
Filtration. Take round filter paper and fold it into half to make a cone as shown here. Fix a funnel on a stand. Wet its side and keep the filter paper in the funnel. Pour muddy water through the filter paper. Clear water will be collected in the beaker below the funnel. The clear water obtained is called the filtrate. This method of purifying water is called filtration.
What happens during distillation? Where filtration is used to separate solids from liquids, distillation is used to use differences in boiling points to separate liquid mixtures. So let's say we have an impure liquid mixture, and then you heat it. Well, one of the substances in the mixture will have a lower boiling point, so that will boil off first. So above the flame, you have the flask, you have the mixture. The vapors are going to be the first impurity that comes out. And then what happens, it goes down the tube, down what we call condensing tube. Cold water flows through there, which then recondenses it back into a liquid, and you get the distilled liquid on the right, and whatever the unboiled liquid would be left on the left.
Let's take an example. Separation of acetone and benzene by fractional distillation. As the difference in boiling points of acetone, whose boiling point is 329 Kelvin, and benzene, whose boiling point is 353 Kelvin, is only 24 Kelvin. Their mixture can be separated by the process of fractional distillation, using fractionating column. Let's see how this can be done. The mixture is taken in the distillation flask. Fractionating column is inserted between distillation flask and Liebig water condenser. The flask is heated on water bath. At a steady temperature of 329 Kelvin, acetone distills out and is collected as first fraction in the receiver. The vapors of benzene are cooled in the column, and liquid benzene trickles down back into the flask. When acetone is distilled out completely, the temperature starts rising, and the receiver is changed. When the temperature becomes steady at 353 Kelvin, benzene distills out and is collected as second fraction in the receiver. Acetone and benzene can be further purified by redistillation using simple distillation apparatus.
Section 3. Elements and compounds. How are elements and compounds different? Substances can be classified as elements or compounds. An element is the simplest form of matter that has a unique set of properties. Oxygen and hydrogen are two of more than 100 known elements. Substances can be classified as a compound, and that is a substance that contains two or more elements chemically combined in a fixed proportion. Carbon, oxygen, and hydrogen are chemically combined in the compound sucrose, C12H22O11. The molecule's model you see spinning here on the right side. In every sample of sucrose, there are twice as many hydrogen particles as oxygen particles. The proportion of hydrogen particles in sucrose is fixed, stays the same. The key difference between elements and compounds: compounds can be broken down into simpler substances by chemical means, but elements cannot. Physical methods are used to separate mixtures, but they cannot be used to break a compound into simpler substances. Boil liquid water, you get water vapor, not oxygen and hydrogen that water contains. Dissolve a sugar cube in water, and you still have sucrose, not oxygen, carbon, and hydrogen. This does not mean that sucrose or water cannot be broken down into simpler substances, but methods must involve a chemical change. A chemical change is a change that produces matter with different composition than the original matter. Heating is one of the processes used to break down compounds into simpler substances. On the left, we have a pan of sugar. As you heat the sugar starts to turn color. It turns brown, and eventually it will turn black. And it's basically going from sugar to burnt marshmallow in 3 steps. The layer of sugar is heated till it breaks down into solid carbon, that's the black stuff, and water vapor. Can substances that are produced when sugar is broken down also be broken down? There's no chemical process that will break carbon down into simpler substances because carbon is an element. When an electrical current passes through water, it is broken down into oxygen and hydrogen. So the first thing is we heated the sugar. The heat caused a chemical change to turn sugar into carbon and water. The water then goes through a chemical change using electricity, which will turn it into hydrogen and oxygen. Right here. We have a simple electrolysis apparatus.
That small plastic container are 2 metal push pins, and they're inserted a distance that's between the positive and negative lead of the 9-volt battery. So you just insert them in there and make sure that they're that distance apart, and that should be fine. In the container is going to be some water that has baking soda mixed into it. The baking soda in the water allows electricity to flow between the 2 metal tips of the push pins. And so now you set them on the leads, and the electricity can flow between the 2 push pins now. And so electricity is flowing through the water, and so that's enough energy to break apart the water, make it undergo a chemical reaction, so that the H2O gets broken apart into H2 and O2. It's going to be hydrogen gas and oxygen gas. And both gases are going to flow up through the test tubes. And one of the gases is going to be in one test tube, and the other one's going to be in the other one. How do you know which one's which? Well, if you take a look at the amount of gas in each test tube, there's going to be twice as much hydrogen gas as oxygen gas. So you can see in the right test tube, you have twice as much hydrogen gas as oxygen gas. This is how experimenters first learned that the ratio of hydrogen atoms to oxygen atoms in water is 2 to 1. It's 2 to 1 ratio, thus H2O.
In general, the properties of compounds are quite different from those of their component elements. Sugar is a sweet-tasting white solid, but carbon is a tasteless black solid. Hydrogen is a gas that burns in the presence of oxygen, which is a colorless gas that supports burning. The product of this chemical reaction change is water, a liquid that can stop materials from burning. When the elements sodium and chlorine combine chemically to form sodium chloride, there's a change in their composition that's also a change in their properties. Sodium is in the dish on the left. It is a soft gray metal. You can cut it with a plastic knife. Chlorine is a pale yellow poisonous gas. Sodium chloride, commonly known as table salt, is a white solid. Can elements be broken down by chemical changes? There's no chemical process that can break down an element into simpler substances. Compounds can be broken down by chemical changes. Deciding whether a sample of matter is a substance or a mixture based solely on the appearance can be difficult. After all, homogeneous mixtures and substances will both appear to contain one. Sometimes you can decide by considering whether there is more than one version of the material. You can buy whole milk, low-fat milk, no-fat milk, light cream, or heavy cream. From this information, you can conclude that milk and cream are mixtures. You might infer that these mixtures differ in the amount of fat that they contain, and that would be correct. Most gas stations offer at least 2 blends of gasoline. The blends have different octane ratings, 91, 89, 87, and different cost per gallon. So gasoline must be a mixture. If the composition of a substance is fixed, then it is a pure substance. If the composition of a material can change or vary, that's a mixture. So since you can buy different fat milks, that's a mixture. Since you can buy different octane rated gasoline, that's a mixture. Since water is water, that's a substance. Now, looking at this diagram, in what 2 broad classes can matter be divided? If you look at the top of the diagram, it breaks them down into mixtures and pure substances. What's the difference between the 2? Mixtures can be separated by physical means. What's the difference between a compound and element? Compounds can be broken down by chemical means. Can a compound be a heterogeneous mixture? No. All mixtures are made up of more than one substances. A compound is more than one element, but it's chemically combined into a single substance. A list of compounds and elements are given. Circle the ones that are elements. Gold is an element. That's good. Sugar is a compound. C12H22O11. Salt is a compound. NaCl. Aluminum is an element. Al. Oxygen, O2. Chlorine, Cl2. Water, H2O. Oops, got 2 elements, so that's not an element, that's a compound. Platinum, Pt. And brass is a mixture. How can you tell the difference between a homogeneous and a heterogeneous? Phases. A homogeneous mixture will have uniform composition, which makes it one phase. Air is homogeneous. You cannot see the different particles that are in the air. Clay is homogeneous because it's the same throughout. Homemade lemonade with pulp, well, that's heterogeneous because the pulp is a separate phase. Oatmeal raisin cookies, that's heterogeneous because you can see the raisins throughout. Finger paint is heterogeneous because whenever you get fingerprints, you can always see the difference in the different layers. Vinegar is homogeneous. It is a 5% solution of acetic acid, and soil is heterogeneous because you can see the different particles. 3 methods that are commonly used to separate mixtures: filtration, distillation, and separation. So if you want a solid from a liquid, you filter it. If you want a liquid from a liquid, you distill it. If you have different colored M&Ms, you could either do it by different colors, or if you have different types of plastic and you have big pieces and little pieces, you can do them by size differences. What do chemists use to represent elements and compounds? Chemists use chemical symbols to represent elements and chemical formulas to represent compounds. So remember, symbols are for elements, formulas are for compounds. Using symbols to represent different kinds of matter is not new. For thousands of years, alchemists used symbols such as the ones on the right. Alchemists and the English chemist John Dalton, you'll learn more about him soon, both used drawings to represent their chemical elements, so you can see them there. The symbols used today are based on a system developed by Jan Jacob Berzelius. He based his symbols on the Latin names of elements, each symbol represented by a 1 or 2 letter chemical symbol. The first letters of a chemical symbol are always capitalized. When there is a second letter, it must be lowercase. If the English name and the Latin name are similar, the symbol will appear to have been derived by the English name. For example, Ca for calcium, N for nitrogen, S for sulfur. There are some of the elements that do not have their symbols matching their name because their Latin names don't match. So for example, lead is Pb for plumbum, like the first pipes were made out of lead, like plumbers, so that's where that came from. Potassium is Kalium, so that's K. Sodium is natrium, so that's Na. So they get their symbols from their Latin names. Chemical symbols provide a shorthand to write the formulas of a chemical compound. The symbols hydrogen and oxygen and carbon are H, O, and C. The formula for water is H2O. Sucrose, C12, H22, O11. Now you'll notice in water and in sugar, you see some subscripts. Subscripts in the formulas tell you how much of each element and each type are there. So in H2O, the 2 is indicating there are 2 parts of hydrogen for each 1 part of water. In carbon, it would be 12 carbons to every 22 hydrogens to every 11 oxygens. Because the compound has a fixed composition, the compound's formula is always the same. The periodic table is a well-known special table that we use to organize our elements. And it's arrangement of the elements in which the elements are separated into groups based on a set of repeating patterns. The word periodic means repeating. The periodic table allows you to easily compare the properties of one element or a group of elements to another element or another group of elements. Each element is identified by its symbol placed in a square. The elements are listed in order from left to right and top to bottom by atomic number, which is a number unique to each element. The atomic number of the element is shown centered above the symbol. Hydrogen, H, is the lightest element and is in the top left corner. Helium, atomic number 2, is in the top right. Lithium, atomic 3, is at the left side and the left end of the second row. Each horizontal row is called a period. There are 7 periods in the periodic table. The number of elements per period ranges from 2 in period 1 to 32 in period 6. Within a period, the properties of the elements vary as you move across the period from left to right. This pattern repeats itself as you move to the next period. That's why it's called a periodic table, because it repeats periodically. Each vertical column is called a group or a family. Elements within a group have similar chemical and physical properties. Note that each group is identified by a number and the letter A or B. Group 2A contains the elements beryllium, magnesium, calcium, strontium, barium, and radium. Now, the meat and potatoes of chemistry is summarized in this section. What we will be doing for the most part this semester is chemical reactions. We talked about physical changes. A chemical property is the ability of a substance to undergo a chemical change. Chemical properties observed only when it undergoes a chemical change. Yes, that is definitely true. What happens during a chemical reaction? One or more substances change into new substances. In chemical reactions, the substances present at the start are called reactants, and the substances produced are called products. A change in the composition of matter occurs during a chemical reaction, always. That's the main thing that differentiates a chemical change from a physical change. In a chemical reaction, you always write the reactants on the left, the arrow pointing to the right, and the product second. For example, I have 6C3H7OH, that is ethanol. I have O2, that is oxygen in the air. And then I have the arrow and CO2 and H2O. So what you're getting here is the reactants are the ethanol and the oxygen. The products are carbon dioxide and water. So when you light the alcohol, you give it the energy to get it started, and now you're seeing the energy in the form of light. And if you were there, you'd feel the heat, and it is turning the ethanol and oxygen into carbon dioxide and water. Now there's 5 possible clues for a chemical reaction. The first one is an energy change. It could be in the form of light, heat, or sound. So what we here have is some glycerin placed on top of a chemical called potassium permanganate. Over time, they start to interact, and you'll see what happens when they do. You get lots of smoke, you get lots of fire, you get lots of heat, you've got lots of energy. So that is the first and easiest way, is an energy change. All that heat that's coming off there, all that light. The second one is a color change. If I start with this sample here, I add the sugar. It dissolves. I add the sodium hydroxide. It also dissolves. I have a beaker of water. I add just a few crystals of potassium permanganate. It's purple. I swirl it, and it dissolves. I go from clear to purple to blue to green. Over time, it turns orange, darkens, and that would be an example of an odor change is another.
Carl, don't you have friends coming over?
Yeah, so?
It stinks in here. You've got to wash this whole room.
Are you kidding? Wash it?
Let's wash it with Febreze.
For all the things you can't wash, use Febreze Fabric Refresher.
The next one is one that you will see once we get to do labs, and it is the formation of a precipitate. A precipitate is a solid that forms from solutions. The first one is showing you the formation of silver chloride from silver nitrate and sodium chloride solutions. Second one is the formation of silver thiosulfate from silver nitrate and sodium thiosulfate. Another one is a gas released. If you put zinc metal in hydrochloric acid, you get zinc chloride and you get the hydrogen gas that comes off of it. Another one, you take magnesium, put it in acetic acid, you get magnesium acetate and hydrogen gas. If you take an eggshell, calcium carbonate, put it in hydrochloric acid, you get carbon dioxide gas. Is the following true or false? If you observe a clue that looks like a chemical change, is it always a chemical change? No. There are physical processes that can show these clues. Like here, if I take some copper 2 sulfate and I start to evaporate the water that the solution is in, the crystals will start to appear and it looks like a precipitate, but it's really just the water no longer being able to hold the crystals. During a chemical reaction, the mass of the products is always equal to the mass of the reactants. The law of conservation of mass states that in any physical change or chemical reaction, mass is neither created nor destroyed. So I look at these two pictures. On the left is the before picture of 216. How do I know mass is conserved? Well, I have two clear vials. And the total mass of the vials and the reactants is 43.43. When I mix them together and place them back on the balance, I see that the reaction has occurred because I have a yellow precipitate and I have an empty vial. But the volume, or I should say the mass, is still 43.43.